color correction, so we will see all of this. Okay, so what is the image formation? So you have an image, and how have you recorded that image? So there is an object in the real world, and somehow this object is illuminated by some source of radiation, and then you collect the rays coming out of that object, and you use an optical system to focus all that energy onto an image plane. And it is very important to formally represent how this process works. Formally means mathematics, so always putting a formula on how things work. And we will go into the details along the course, but knowing how the image is formed is extremely important, especially when you want to invert it, because very often this optical system degrades the image. And if you want to restore the original image, so to undegrade the image, if you want, so you need to know how the image was formed. Then, there is a light source, so the general word is the sun, and then the sun illuminates the object, and then the rays coming out are focused through some lens or some kind of optical system. And probably you know already this from optics, so that optical systems, all lenses invert the image that they form. Is doing that, but somehow our brain is also correcting for that. But this is a real image. So this is the image that an analogic image that would be formed. So it is defined for every possible point in the space. You would have a different amount of light coming in. So this is the real image, but in the computer you cannot have a real image. So in the computer what you have is a quantized image. So you will have to record that image that exists in the real world through some camera. Now we use digital cameras for that. And then digital cameras have to discretize a space, because we cannot record absolutely every point in the space, in a continuum. So we have to discretize a space, and we have to discretize the color. So in the color, it is the same. We cannot represent absolutely all colors in the real world, but we discretize the color. So the image that we'll record is this one, rather than the continuum that is formed in the real world. So that is the value that we will have in the computer. So it is discretized in space, and it is discretized in color. And here is a presentation of how we can discretize in color. So let's say that we have a continuum of colors, and then this continuum of colors, here it is exaggerated just to be able to see it. But in these continuums, we assign all these values to this color, and then all these values in this range to this color, just a single one, and all these colors just a single one. And we construct our stair, and this stair is also present in this monitor. So all this that seems to be a continuum, actually it is not a continuum. It is just it is discretized, but it is discretized in so fine steps that we don't notice. But it is discretized too. So so just to review the whole process again. So there are a couple of operations. One is sampling in space. The other one is quantizing the color. So if this is the real image, we have to sample in space. So we divide the real image into small squares that are called pixels. The pixel is pixel for these. So this pixel is picture. This is part of the world. sequential element. Then from these two parts, we have formed the word pixel. So we divide the space into pixels, and each pixel is averaging the color that it has inside. So this pixel here is the average of all these colors, and this pixel here is the average of all these colors, and so on. And at this average, again, if this is a continuous signal, this average will also be a continuous. So it can take any value. But in the computer, you cannot represent any possible real value. So you have to quantize the colors too. So at the end, what you have is a sample and quantized image. That is the one that is represented in the computer. And we will also see, we will present this tomorrow. So what is a digital image? So a digital image, so here we have these picture elements here. So a digital image is an image that if you make a zoom very fine, so you would see that it is made of squares. So each square has a pixel length. So it is the distance between one pixel and the next in the digital camera. So what we are seeing here is the distance between two different sensors in the camera. And then each one of those sensors will be able to represent colors using a color code. And the most common color code is the RGB. So it is the red, green, and blue channels. So you have 3 channels, and you represent a number between 0 and 255. And 0 and 255, because if you use 8 bits, you can represent numbers between 0 and 255. So let's. I have entered into that. So let me try to mess it up. Go up. So let me go to the whiteboard. Okay, so if we will represent colors in an G, G. So each one of these will have 8 bits. And each one of these 8 bits will have a value 0, 0, 1, 0, 1, 1, like that. So with this, if you have 8 bits here, you can represent 2 to the 8 minus 1. This is the maximum value that you can represent. And you go from 0 to that. So you go 0, 1, 2, all the way to 255. So each one of these values, arguably, it will go from 0 to 255. And this one to 255 and 755. And these are called channels. Let's see if I can choose a different color. Okay. So these are called channels. So a color image is nothing more than an image that has some channels, and within those channels we have values. So I'm afraid that I'm messing with that all the time. So this is not a good idea. Press this thing. Software. Okay, so now we go to slide presentation again. Yeah. So these are the numbers that we are representing in the RGB channels. So this color here is represented by 206, 128, and 9. then this is the next color, and so on. If you have a gray image, and if you put the three numbers to the same value, then you have a gray value. So if you make this one, if you make the three channels to be the same, you make R equal G equal D, then what you have is gray. So you go from 0 to 55. So this goes from 0 to 55. This is black. This is white. Okay, and this is by convention. Okay, so we all agree that that is a way of representing images. But you could have a different agreement. Okay, there are contexts where you have different agreements. Okay, so now we will present along the course how to deal with colors, also how to deal with gray images. And then we will revolve around colors again. So we have the three channels, green, red, and blue. And then depending on the values that you put in both, so for instance, let's say I did red equal green equal blue, but if you make red equal green and then set blue to 0, what you have is yellow. Okay, so yellow, and all the colors in yellow, you can achieve by making this one. And then if you make red equal green and then blue equals 0, all these colors are all the yellow colors that we have. Okay, so you have all these values from 0 to 55. Then you have a whole range of yellow colors. Okay, so we make red equal green and blue equals 0, and then we have yellow. And you might have different tones of yellow. And the same for magenta, the same for cyan. And then any color in general, red and green and blue channels will have different values. Okay, then we will explore a bit how to display images. And we will see a very old technology, these cathode ray televisions. But these CRT monitors, they're old, but they show very well possible technology. So how we can combine. So actually, technologically, you don't need to display colors. So to have a layer that knows how to represent colors, all you need is how to represent three different colors, the red, green, and blue. And then you will have different intensities in each one of the pixels. But these pixels are so small that you don't see them. So when you look from distance, then you don't see the pixels anymore. But what you see are the different colors combined, because somehow you are not able to see the details from the distance. And then we will do operations on the images that we will call point processing. So this is the original image, and then at every point we will do a different modifications. We can increase the brightness or decrease it, increase the contrast or decrease it, increase something that is called gamma that we will see for the V's, or decrease it, or we can play with the histogram. We will see all these kind of operations, but these operations are made point by point, so that is why they're called point processing. Then we will also explore a bit how we perceive colors, so how our eye detects the colors, and then you have there a couple of videos sensors of how the human retina works, or how images are formed. Then we will explore a bit, again, the physiology of perception, and these are cells that detect different kind of lights. So also we have detectors that are tuned to red light, green light, or blue light. And we will see how they are organized in the eye, and what are the response curves of those kind of cells. And we will play with our sensors and change the colors to excite the neurons in different ways. And then we have been talking about RGB, but it is not the only way of representing a color image. So you can also transform this RGB into something that is called luminance, hue, and saturation. Hue is a tonalidad in Spanish. So you have an intensity channel. So this is how many photons are arriving from that area, while this one describes the color of those photons, or what is the wavelength of those photons. So this is a different representation of this one. So this one is how many red, how many green, how many blue, or bluish photons are arriving, while this one is how many photons in total, and then somehow you characterize the wavelength of those photons. And actually, the eye sees in RGB in a way, while the brain sees in this way. Okay, so this conversion is also done through our brain. Okay, so then we will explore a bit how this conversion is performed in our brain. We will be very interesting experiments to see how our brain is more sensitive to some kind of changes than others. This is the same. And then we will do these point operations one now with colors. Then we can do it in any one of the bands. We will also do color transformations. So let's say that you have a degraded image like this one. So this is an old image, and somehow the paper has degraded over time. And then we will apply some transformation to restore the colors to the real colors that they should. And then we will be able to do this computationally. So we have to find a function that maps colors from this space, colors in this space. So for instance here, you see that if this is the RGB code of this color somewhere there, we want to transform this one into this one. So the RNG channels don't change, while the blue channel, we make it brighter. So we are lifting the blue channel, and we have to find this function that lifts the blue channel by the right amount. Okay, then we will see the 2D Fourier transform. So the 2D Fourier transform is an extension of the 1D Fourier transform we are familiar with. So you know that we have the Fourier transform and the inverse Fourier transform. So the Fourier transform takes an image and transforms it into the frequency space, while the inverse Fourier transform does the opposite. So it takes the image in the Fourier space and transforms it into the real space. So this is the real domain. So this is how we look at images, and this is how the image looks like in the Fourier domain. We will explore all that. There's this formula. What is the name of that formula? I'm sure you have the same formula in 1D signals. So, which is the name of that? Discrete Fourier transform. So the Fourier transform has kind of family names, so qualifiers. So this is the discrete Fourier transform. It is discrete because you have a finite set of frequencies and also a finite set of pixels, spatial location. Okay. Then, okay, so in the Fourier transform, one of the key elements is the sinusoids. So how does a 2D sinusoid look like? So we will explore. Okay, so what is a two-dimensional sine? And then, as in the one-dimensional sines, they will have an amplitude, they will have a period, and they will have a phase that is here. So the phase is not represented in this diagram, but will shift the wave to the left or to the right. And then now it appears something that doesn't appear in one dimension. So now in two dimensions we can have orientation. So this wave propagates along this direction, while we can turn the wave and it can propagate in this direction. So now this orientation is something new that 1D sinusoids don't have. Okay, so now this is we have turned the wave. And here it is represented the shift. Okay, so here we have zero shift. Here we have a shift that is different from zero. So we have zero shift. The maximum is at the origin. While if you have some shift, phase shift, now the maximum is placed with respect to the origin. And the Fourier transform, you know, it is a complex valued function. So that means that when you take a real valued image and you do the Fourier transform, the Fourier coefficients are complex numbers. So if they are complex numbers, they will have real part and imaginary part. So you can, if this is the frequency plane, so for every point, for every frequency, you have a real part and you have an imaginary part. And if you have real and imaginary parts, then you can also represent it in a polar representation with amplitude and phase. So we will explore all these. And then we will relate all these issues of phase, frequency, wavelengths, and so on. And we will do the Fourier transform of images. So we have an image, and now if you have a Fourier transform, you will have for every frequency, so this plane is frequency, and then you have an amplitude for those frequencies, and we will also have a phase. So this phase is this phi, what is it? This phi here, this angle. So when you make the polar transform, the polar representation of that Fourier transform. So this is phi, this is the amplitude. And we will learn to interpret these diagrams. And yeah, this is the continuous. So we will have different versions of the Fourier transform. So we have the continuous Fourier transform. So in the continuous Fourier transform, the images are continuous. And then instead of sums, we have integrals. And the same for the frequency. The frequency is also continuous. And then we will have the discrete Fourier transform with summations instead of integrals. And then we will explore convolution. So convolution is already an operation that you have in your background. So we will also convolve images with kernels and then to produce something. And this kernel is blurring, which is not very useful, but we can also use kernels to unblur our images. And then we will explore a bit the mathematical properties of Fourier transform. And one of the most important ones is that the Fourier transform of a convolution is the product of the two Fourier transforms. And because of the duality, the Fourier transform of the product is also the convolution in Fourier domain. And you have also this concept of aliasing. So if you have a sampling frequency that is not high enough, then you will have aliasing in your signal. And the same happens with images. So if the pixel size is not big enough, it's not small enough, you will have aliasing, and then you will have overlapping spectra, like in this plot, while if the sampling rate is fine enough, then you wouldn't have aliasing. So the spectra would not overlap, and we will explore all this again. So it is not something that you have to understand just now. That's simply the concept, that the same concept of aliasing that you already have. It will happen also with images. And here you have an example of this aliasing. So you can imagine that the front of this frame cannot look like this, with these kind of jagged borders. Should be more something like this, even if we don't see the details, but the details cannot be these. So this is actually aliasing. And then we will also learn to resample images. So let's say that you have an image and you want to make it larger or smaller. So you are changing your pixel size, changing the sampling rate, and then we will learn how to do that, and we will learn different techniques, nearest neighbor, cubic interpolation. We will learn a few of them. Bilinear interpolation, it is not represented there. And also these tools to resize images will be helpful to apply geometrical transformations to images. So if you take an image, you can computationally rotate it and apply any geometrical transformation. So the rotation is one of them, but also warping is another one. So let's say that you are given this image, and now within the computer you can make it, you can change the kind of the layout of the image. So you see these two lines are not parallel, you can make them parallel, for instance, inside the computer. And we can stitch images. So for instance, let's say that you can take a few pictures of something, and then because of the projection geometry, if you simply overlap them, they don't really match. So you have to deform a bit one of them to match the other one, and then we will be able, through these geometrical transformations, we will be able to deform this a bit so that it matches the second one. And then we will do Fourier filters. So in the same way that you have done the Fourier transform and you have designed filters in the Fourier domain, we will be able to do that, but also now with images. So let's say that you are given this image, this is the power spectrum of this image, and now you apply this filter, and then what you get is something like this. So this is the filtered version of this original image, and this is the filtered power spectrum. And you can do low-pass filters, high-pass filters, and then high-pass filter. We will learn that high-pass filters are useful to detect the small details. So we can also kind of combine high-pass filters with original images to produce something that is more sharpened. So let's say that you are given this image, so the original is lost. This is all you receive. You can enhance this one. It is a little bit artificial. You see that there are some kind of rippling around, but it is much sharper than this one. You see better the edges of that image. We will do that through high-pass filters, band-pass filters. We will also use them. That will be, we will present an operation that we will call unsharp masking. These filters can be used to simulate movement of the camera, or also to correct for movement of the camera. So if the camera is moving, now using these filters, you will be able to correct the movement of the camera. We will design tools to reduce noise. So let's say that you have this image, and this image has a lot of noise, And then we will explore different ways of trying to remove that noise. And yeah, different, for instance, this Wiener filter is a very effective tool to do that. Let's say that the original image is contaminated by some kind of regular pattern. So we will design filters to remove these regular patterns. And the same for this kind of noise that is called salt and pepper. It is called salt and pepper because it has white and black points. They're coming from malfunctioning of the camera. So let's say that you have a camera, you take a picture, but one of the sensors is dead. So if that sensor is dead, then it will never record the amount of photos arriving. It will record 0. And the same may happen because it's dead in a different way. It is there is a short circuit there. So instead of just reading 0 all the time, it reads 255 all the time. And then we will learn some techniques to remove those bad pictures, and then more ways to remove them. All these will be called nonlinear filters. So all the filters that we will apply in the Fourier domain, they are called linear filters, and linear filtering is associated to convolution. But we will also learn a few nonlinear filters. One of the most important nonlinear techniques is this binary morphology. So in binary morphology, we will take an original image and we will define different operations. Some of them resemble a bit like convolution. We will see the details in the future. But some of them resemble a bit like the convolution. So it is like, for instance, dilation is like convolution. So if I convert this image with an L, then this is a delta point. This is a delta point. So this is kind of delta function. So the delta convolved with an L is an L. So this is actually, dilation is the most similar to convolution. But we will not only define convolution, but we will also define erosion, opening, closing, dilation by something else that we will define in the future. And we will use these tools to restore binary images. So let's say that we have this contaminated image, then we will be able to remove the parts that have been contaminated and recover the most stable part. And the same with grayscale images. So this is just black and white images. But then if you have a continuous of colors or grayscales, then we will also define these operations for that, those kind of images. Then we will use them. For instance, here we can see that we are kind of restoring the different contrasts. So this area is very dark, now it is less dark. We are highlighting some features in the background. We can do this kind of stuff. And then the last lecture will be on compression, image compression. So when you take a picture, if you count how many bytes you would need to represent those colors. So let's say that we have almost 5,000 pixels, so 5,000 in each direction, and you need 3 bytes for each one of the pixels because we need the RGB components, and each one of them takes a byte. So the full picture takes about 100 megabytes. But now we can reduce that 100 megabytes to as low as 12 kilobytes. So we are making a reduction by 4 orders of magnitude. So this one has 10,000 less values, coefficients, than the original one. But still, we don't see the difference. So we will learn techniques to do this. This is how cameras and your phones keep the images in memory. Yeah, so here is just a zoom to show that there is not a very noticeable change between something that is the full size and something that is has 10,000 fewer positions than the original. And so this will be it. Any question? No? Okay, so it will be a very basic course. So all these techniques are very, very simple. Some of them will involve a little bit more mathematics. We will explain them, but they are very simple techniques. And you're an engineer, so whenever you make an exam, you have to talk about two things. So one is the technique itself, and you have to talk about it in English, or Spanish, or whatever. So just pure text. But all these techniques, they involve mathematics, and that is another way of conveying ideas, and you have to use that language too. So in the same way as you use English, you have to use the mathematical language, and you have to explain this formula means this. You have to use formulas properly. But one of the main mistakes that students do when they do exams is that they don't talk about the mathematics. So mathematics in this context are extremely important. Most of my time, I will be explaining the mathematics behind the things. So those are the concepts that are more difficult to grasp. Whether we are denoising or making images smaller, okay, that's very simple. Everybody understands that. But not everybody understands how mathematically you do that. So in our course, we will have 3 parts. So in general, in image processing, you have 4 parts. In this course, we will cover 3 of them. So that is a part that is the problem that you want to solve. So there is a problem that you want to solve. And how you solve it? The first step is find a mathematical way to solve it. And we will discuss a lot about this during the course. But once you know what is the mathematical also means in algorithm, so you want to find a sequence of steps that solves the problem. But once you have found this mathematical way, you have to implement it. So you need something to run it. And we will see that a bit, but not so much, in the sense that so you have to program it. So you have to program it. And this program can be software, but it can also be hardware. And this course will be about this. So this course This course will be about this. We will see a bit, but only a bit about this. So our main problem will not be programming this. This is the 1.5 extra points that I have given you in the practice. But our main thing is this one. So understanding the problems and understanding the mathematical ways of solving those problems. So whenever you do an exam, be very careful about mathematics. And there's another very interesting part that we will not cover at all. But is the same way that you can run this program on general computers, you can design a specific hardware, just one algorithm that does image processing stuff. And you can implement this in hardware, and then it is very, very fast. And all your phones, they are doing that. So they have a specific circuitry dedicated to image processing. But for this, you have to be proficient in for this one. So for this one, you have to be proficient in electronics, but it's not part of your main specialty. Also in programming. You have to program. Actually, do you remember that in the IEEE list of interesting topics, one was image processing. So image processing is at this level. Choose the right color again. So the first topic was image processing. Image processing is here. There were a bunch of topics related to deep learning, machine learning, and all those. So I will in general call them data analysis in general. They refer to all those kind of techniques. So they are, most of the most important techniques are here. There was one that was, choose the right color again. There was one that was VLSI. VLSI is here. Internet of Things is here. Internet of Things is there too. There was another one, antennas. Antennas is here too. It is more dedicated to communications rather than just image processing. They're somehow related. They're all, so at the end, all these things, they are processing signals. And an image and a signal is the same. We will learn that tomorrow. So an image is nothing more than a signal. Okay, so this is the course.